Hello, I wanted to take a moment and go through Lab 2.05 with you real quick. So as you can see, I have the lab up. If I scroll through the lab, it gives me the ocean water density lab video. Okay, so I want you to view that. And then it also gives me the data from the video. Now in the video they are taking 3 samples of water, fresh water, salty water, and saturated water. The fresh water has no salt in it, the salty water has some salt in it, and then the saturated water has the most amount of salt the water will hold. It is fully saturated with salt. So they have provided us with the data for the lab. This is not something that we have to go find on our own. If I continue to scroll through the lab, question number 1 says, how will the ice mix with the salty water? And it wants us to write a hypothesis for each of these solutions, which is fine. We can do that. I'm going to go ahead and bring up the lab PowerPoint and go through a few things with you in order to be able to write that hypothesis. So in the lab we watched an experiment where they made 3 solutions. They had a temperature reading at the bottom of the solution and a temperature reading at the top of the solution. In each solution they placed a cold or a red ice cube. The ice cube acts as a glacier. The solution acts as the water the glacier is melting into. The reason it's dyed red is if it was just a plain ice cube, we would not be able to see the movement of the cold water through the solution. So because it's red, we can see how it moves through the solution. So now we're on to that part of making our hypothesis. So what's going to happen to the cold red water as it melts through the different solutions? Now we know that density changes when we add salt to a solution. So we know that there's going to be a density variance between that fresh water, the salty water, and the saturated water. But how is that going to interfere with 1, the mixing, and 2, the temperature? So I have placed a hypothesis on the board for the mixing and the temperature of the fresh water. You will do your own hypothesis for salty water and saturated water. So my hypothesis to describe mixing is, if I place a red ice cube in a solution of warm fresh water, then it will melt and mix evenly throughout. So that is my hypothesis. My hypothesis to describe temperature is, if I place a red ice cube in a mixture of warm fresh water, then the top will be colder than the bottom. Now this is just a hypothesis. It doesn't have to be true. It doesn't have to be correct. We're going to look at the data that the science has provided for us and decide what really happened. This is just what I think. If I do this, then this will happen. So you're going to come up with your own hypothesis for salty water and saturated water. Something for an example, if I place a red ice cube in a solution of warm salty water, then it will melt and blank. Do you think that it will stay at the top? Do you think it will stay in the middle? Do you think it will stay in the bottom? Do you think it will mix evenly throughout? On to the temperature. If I place a red ice cube in a mixture of warm salty water, then the top will be blank than the bottom. The top will be the same as the bottom. The top will be colder. The top will be warmer. What do you think? And the same for the saturated water. If I place a red ice cube in a solution of warm saturated water, then it will melt and blank. Stay at the top, float to the bottom, mix evenly throughout. Hypothesis describing the temperature mixing of the saturated water. If I place a red ice cube in a mixture of warm saturated water, then the top will be blank than the bottom. Colder, warmer, or the same. And that would be your hypothesis for each of these solutions. Now, looking at number two on your lab is blank, right? But they have provided the data for us, and I'm giving it to you. So all that you have to do is transfer the data onto your lab and add any additional observations you may have noticed while viewing the lab or the lab video. So here's the data for, and you can just pause this and copy it down if you'd like. Here's the data for the fresh water. Here's the data for the salty water. And then here is the data for the saturated water. Now what I'm going to go through with you, and like I said, if you need some more time, just go ahead and pause the video, is I want to go through and analyze each of the data for each solution with you to describe the mixing and the temperature. So once we go through and analyze what happened, we will either be able to support our hypothesis or refute it. So our hypothesis will be correct or incorrect. Let's first take a look at the fresh water. We can see that at 0 minutes, the ice is at the top. The colored melt water from the ice cube began to sink immediately. Temperature at the top and bottom was the exact same at 60 degrees Celsius. At 5 minutes melt time for the fresh water, the ice began to sink to the bottom rapidly and mixed with the water as it sank. The bottom of the glass appeared to be slightly darker, but there was no distinct boundary between the top and the bottom of the glass. At 10 minutes, the ice had completely melted. The bottom of the glass was slightly darker than the top of the glass. And then the same thing was found at 30. Now, temperature at the top of the glass at 30 minutes was 40 and the bottom was 35. So the top ended up actually being warmer than the bottom. So that was different from my hypothesis. I thought the top would be colder. Now, if I think about how density changes with, make this better so we can see it a little bit better in our video. How density changes with temperature, how density changes with salinity. I should have known about these temperature variances, right? If I'm looking at the lab, it wants me to understand how cold water mixes with warm water when we add in different scenarios. So we are definitely dealing with different density. So I know that cold water is denser than warmer water. So I should have known that that cold melt water, that cold red water would sink to the bottom. But that's okay. Now I do know that. So when I'm answering question number 3, because this is the first part of question number 3, I'm going to say, and it's provided there in the data. If we look up here, the bottom of the glass is slightly darker than the top of the glass. So how did mixing occur after 30 minutes in our fresh water? After 30 minutes, the bottom of the glass was slightly darker than the top, but there was no definite line of separation. If we look at the temperature, based on the data, remember this is all given to us in the data, after 30 minutes, the top of the glass was 40 degrees Celsius and the bottom was 35. So that is different than my hypothesis. So this is question number 3. You can see that here. I put the question there on the screen. All right, let's do the second part of question number 3, which is analyzing the salty solution. So at 0 minutes, the ice is at the top. Meltwater from the ice cube floats on top of the saturated water. That's different than what we saw in the unsalted. In the fresh water, it sank automatically. After 5 minutes, the top of the glass is significantly colder than the bottom at 35 degrees, and the bottom is at 55. But there is little to no mixing. The colored meltwater is staying at the top. After 10 minutes, a little more than half of the ice is melted. So at 10 minutes in the fresh water, all of the ice is melted. At 10 minutes in the salty water, only about half of it. And the meltwater is staying at the top of the glass. There is some mixing throughout, but most of it is staying at the top. And then the top is actually, again, even more colder. After 30 minutes, all of the ice is melted. Most of the meltwater stays in the layer above the salt water. The salt water shows some color. So there was some mixing, but most of the red ice cube stayed at the top. And so that's what we're going to put for the second part of question number 3. The cold red water stayed mostly on top of the salty warm water. There was minimal mixing of the two. If we then look at temperature, we can see the top of the solution after 30 minutes was 30 degrees. The bottom was 50 degrees. Top was much colder than the bottom. I mean, in the first scenario, we saw a difference of 5 degrees. In this one, there's a difference of 20 degrees. So let's take a look at our final solution. We're kind of seeing a trend here, right? Less mixing and more of a temperature variance with increased salt. So that would be increased density of the warm, salty solution. After 0 minutes, the ice is at the top. The meltwater from the ice cube spreads out from the ice cube but does not sink. After 5 minutes, there is very, very small amount of mixing. It's mostly staying at the top. After 10 minutes, the ice is melted. Colored meltwater mixes with the fresh water at the top of the glass. The bottom of the glass shows little to no color. And then after 30 minutes, all of the ice is melted. There is a thin layer of cold meltwater on top of the salty water. So after 30 minutes, we can see that there was almost no mixing. After 30 minutes, the cold fresh water, because remember the ice cube really is that fresh water, the cold fresh water from the ice cube stayed at the top of the solution. If we then look at the temperature difference, the temperature for the salty water was only 5 degrees colder than the bottom of the glass. So not a huge temperature difference. All right, so I'm going to switch these slides because we did the saturated water second. So if we go through each of these, we can see that for the fresh water, lots of mixing, not a huge difference, temperature difference between the top and the bottom. The salty water, a little bit of mixing, so that would be this middle one. A little bit of mixing. Um, Most of it stayed at the top. Oh, that's the saturated water. Okay, there we go. There's the salty water. So the salty water, a little bit of mixing, not a huge temperature variance, but there was definitely a line between that cold water and warm water. All right, our last one, our saturated water. Almost no mixing and a huge temperature difference between the top of the water and the bottom of the water. Let's look at question number 4. What does the experiment suggest about what happens when icebergs melt into the ocean? Because really, that's what we're looking at, right? That red ice cube is a glacier and the solution is different seawater, right? Because we know seawater has different salinities based on latitude. So that mid-latitude region definitely has a higher salinity. What does your experiment suggest about icebergs melt into the ocean? So when an iceberg melts into the ocean, the top of the water would be fresh, less salty, and colder. Based on our data and observations, the cold water stays at the top and does not mix with the salty water. So the sea surface temperatures would be colder than We'll just put that. The sea surface temperatures would be colder. Okay, so I hope that you have found this video helpful. It's definitely a little bit quick, but if you continue to have questions on the lab, please let me know. Here are the directions to get into Dropbox if you need them. And like I said, if you continue to have questions, please let me know.